Hello everyone, today we are going to continue discussing the MOSFET DC analysis. Last class we discussed together the load line and how can we draw the load line for MOSFET with any parameters, and we fastly discussed this example. So we are going to continue solving these examples in more detail today and discussing the MOSFET operation in driver mode or load mode. So here, this example, it's required to determine the transition point, which is the point, as we discussed here, this point, which is the point that is going to split the saturation and non-saturation mode. So as we can see here, this point is called transition point, and the region here is non-saturation, and this region is saturation mode. So it's required to determine this point. So again, how can we determine this point? In order to determine this point, we need to identify three things actually. One is VDS and the value of ID and the curve of VGS, which is going to pass with this point. So if I just draw the line here like that, it will be like that. So we need to identify this point. Okay, so we suppose that we have another curve here for VGS. So in order to know this point exactly now, we need to identify three values: the curve VGS, okay, and the value of drain to source and drain current. So this, how can we identify the point of operation, or sorry, the transition point. So this is our MOSFET here. We have resistance R1, we have resistance R2. So all of these values are known. We have RD is given as well. And finally, the source is connected to ground. So this is the analysis for common ground, a common source MOSFET. In order to calculate the relation or get these points, we can substitute either in the ID equation in saturation or non-saturation mode. Because as we can see here, this point here now, guys, this point can be the start of the line in saturation mode or the end of non-saturation mode. So you can use both of relations, both of current relations we used before. So in this case, we can use the saturation current and substitute with the value of V drain to source in this equation in order to get the point of intersection. So we have now this curve, and we have the curve of VGS at the locus of saturation. So the locus of saturation would happen all of time if VGS minus VTN equals VDS saturation. So we can say if VDS equals VGS minus VTN, so this would be saturation point. Okay, so this would be the saturation point or splitting point or transition point. So now we need to use the two equations as we said. So firstly, we can say now the relation of current. So we have ID equals Kn times VGS minus VTN squared. So this is the relation of current with VDS at saturation mode. And we have the other relation from the circuit here, which is VDD equals ID times RD plus VDS. So we can say from here, ID equals VDD minus VDS over RD. Okay, so starting from the VDS equation, so we can say now VDS equals VDS saturation at the point of the saturation. So it's VGS minus VTN, which is equal to the same circuit equation, which is VDD minus IDRD. Now, substituting in the equation, which is ID as we said, so we can now make another equation. So substitute with ID in this equation here. So we can say now VDD minus Kn times VGS minus VTN square times RD equals VGS minus VTN. So this is VGS minus VTN. This is the left-hand side of the equation here, okay? And this is the right-hand side, VDD minus Kn times ID, which is, Kn times VGS minus VTN square, which is ID times RD. So this is now just, we substitute the two equations together here in order to make one quadratic equation. So this quadratic equation, guys, can be solved. Even when you try to solve this equation, you can simplify this equation. So instead of writing the terms VGS minus VTN, you can give it symbol, for instance, like A. So we have now A square plus A minus VDD as a constant, okay, and here we have Kn times RD times A square plus A minus VDD equals 0. So this is a quadratic equation now, and this quadratic equation, we need to get the roots, which are A1 and A2, and we can get it from the equation as we discussed earlier. How can we get the roots of quadratic equation? So now, guys, substitute with the constants we have. Finally, we will get two solutions. One solution would be accepted and the other solution is not accepted. Most of time, guys, the other solution either being like a negative value or another value which is in a non-saturation region, and we now consider this operating point as the intersection. So in this case, we can consider this value, which is 1.35. So this is our VDS now. So VDS equals 1.35 volt. And we know that VGS equals VDS plus VTN. VTN is given, so we can substitute by VTN. So VGS now equals 2.35. So if I would like to represent the curve now, so assume this is our curve at VGS equals 2.35 volt. So in this case, the operating point or the transition point is at certain current and certain volt. So the volt magnitude, which is VDS, we got VDS, which is the saturation point, equals 1.35 volt. And we need to get the corresponding current. In order to get the corresponding current, just substitute again in the equation of ID. So again, substituting the equation of ID, so we can say finally here ID equals 0.1, which is Kn, times VGS minus VT, which is nothing but now the saturation volt, which is 1.35 squared. So the current is 0.182. So this is the current of 0.182. And this is also the point of saturation, which means if you have many curves at different values of VGS, so the saturation curve would appear like that. So this point now, the Q point is the same as our saturation point. Why again? Because we use the two equations, which are the current equation. So we use the current equation at saturation level, which is already one of the points on this curve, and we substitute at the same time with the value of VDD minus IDRD equals VDS saturation, which is the point of transition here between non-saturation and saturation. So now we could identify the point of transition. Now, after understanding the DC analysis of common source and also dual supplies, as we discussed in the previous class, let's have another topology, or let's say configuration for our MOSFET. What will happen if we connect the gate point to the drain point? So if we make a short circuit here, what will be the performance of our MOSFET? Let's see together. So in this case, guys, we can say now for enhanced MOSFET connected in figure here, okay, we can consider it as nonlinear resistor. Why? Let's see together and investigate why it can be a nonlinear resistor. A transistor with this connection is called an enhancement load device. Why load? Again, because it will represent a resistor. Actually, we have VDS saturation equals VGS minus VTN. But here, V drain source, which is the volt between this point and that point, okay, equals V gate source. Why? Because the gate point and drain point are equal now. This is the gate point and this is the drain point. Since VD equals VG, so we can say VGS equals VDS. It's making sense. So since G point is the same as D point, so we can say VGS equals VDS. So if VGS equal VDS, so this means what will happen to our curve? You can find that substitute here in our relation. So ID equals Kn times VGS minus VTN squared. So it can be now, instead of VGS, we can say VDS minus VTN squared. So this guy is going to shift our curve. Why? Because you know the saturation is already equals VGS minus VTN. So in this case, VGS equals VDS. So in this case, the curve would be shifted by this value. So this would be now the new characteristic for our MOSFET, okay, which can be represented as a resistor characteristic, okay. So this is the driver characteristic now. Let's see what would be the performance of this load device if we connected this device to another MOSFET. So in this shape here, we have our D MOSFET or load, okay. Let's say L MOSFET. So this is ML MOSFET L, and this is MOSFET D. So we refer to this as load because, as we discussed, the drain and gate are connected together, okay. And this is regular MOSFET, but we are going to say this is like driver MOSFET. Why? Because it's used in applications of driver and inverters. So this circuit is used mainly in drivers and MOSFETs. We will see, in drivers and inverters. We will see an example and discussing in detail why this circuit is called inverter. So let's analyze the circuit here together. So what will happen if we add a certain voltage magnitude here, VI? What would be the shape of V out for this circuit? Okay, let's see together, guys, in this example. So in this example here, we supply the drain by 5 volts, and we will apply certain voltage magnitude here at VI and observe the output volt, okay? And we have here the two transistor or two MOSFETs parameters. So VTN-D, which means VTN for driver, the second MOSFET, equals 1 volt. We have KND equals 50 microampere per V square. We have KNL equals 10 microampere per V square, okay? And assume lambda ND and lambda NL equals 0, so we are not going to consider the effect of resistance. The subscript D in this problem refers to the driver, and subscript L refers to the loads. Okay, so we need to investigate the performance of this circuit. What would be the output volt here if the input volt is firstly 5 volt, then 1.5 volt. Okay, so in this case, let's find one important thing, one important concept we need to consider. This circuit is going to be used for inverters, and it's very well known. For inverters, guys, inverting means when the inverting means the active high signal would be converted to active low signal. So if you have active high out input, which is 5 volt here, we can consider it as active high. Why we consider this as active high? Because already the input supply here for this circuit is 5 volt. So we can consider this as active high signal. So 5 volt for an inverter circuit with resistive loads, when the input voltage is large, which is 5 volt, so the output volt drops to low. So we expect that the output volt would be low, because inverter means if you apply active high, the output will be active low. So since the output volt would be active low, therefore we assume that the driver transistor is biased in non-saturation region. So once, guys, if we assume that the input volt is high, so the output would be low. If we go to the circuit here again, so the output here would be low. This volt would be low, which means now the value of VDS here would be low, and value of VDS would be low. This means the drain source is small value, which means it's a non-saturation in the curve, because if you remember, this is the shape of our curve, this is the characteristic, and if we are working in the non-saturation, so the values of VDS will be small. So VDS are small values in non-saturation region. So once we applied the 5 volt here, we can say, once we applied 5 volt in input here, okay, so this is going to be active high signal. In this case, we can say, since this is inverter circuit, the output volt would be low. If you consider it's working in saturation, it would be wrong. So you have to repeat the problem again. So it's now a kind of, it's taking more time to get the solution. However, if you know the circuit by experience, so from the beginning, you can assume the right solution. So based on our experience now, since this circuit is going to be used for inverter, we know the output volt would be low if the input is high. And in this case, this means VDS is going to be low. And we can consider in this case, it's going to work in non-saturation. Okay, so this transistor is going to work in non-saturation. Take care that the current of the upper transistor and lower transistor is the same current. So I drain load equals I drain driver. So this means we can now make two equations. One equation for the drain current here in non-saturation region, and the other one here in saturation, because all of time, this load is going to be in saturation region. So this is the characteristic of that circuit, since VDS equals VGS. In this case, guys, we can now say the current equations, I driver equal I load, and you have the non-saturation relation for our current, but this is for D MOSFET, driver MOSFET, and you have the saturation current for the load MOSFET. Okay, so again, this is for non-saturation, and this is for saturation. This is for driver, and this is for load MOSFET. Now, just substitute with the values available in our example here, okay? So we can say now VGS of driver equals Vn. Let's go to the circuit here and see that again. So VGS of driver, which is this volt, VGS equals Vn. Why? Vn is our source here, and we get to source because the source is connected to ground. So we can say V input equals VGS. And V drain to source of driver equals V out from the circuit here again. So this is V drain to source. So drain to source here, this volt, is nothing but our output volt. So substitute in our equation here, and also know that for load, we have gate to source volt equal drain to source volt all of time, which can be obtained from the circuit here as VDD minus V out. So here, as you can see, this volt here, VDS of our load, equals 5 volt minus the output volt, or VDD minus V out. Now, substitute with in this equation, guys, so we can get the relation Kn for driver equals 2V input minus V to ND times V out minus V out square equals Kn load times VDD minus V out minus VTNL square. Now, substitute with numbers. So everything is well known except V out. So take care here, we substitute Vn equals 5 volt, okay? If you would like to make a general equation as a function of Vn, so keep Vn as unknown, and you can use it to draw the relation between Vm and V out, as we will see in simulation later. So now we have one equation and one unknown, but this equation is quadratic equation, so we can get V out from this quadratic equation. So finally, the simple form of this quadratic equation is 3 V out square minus 24 V out plus 8 equals 0. We have two solutions here, actually. One solution is 7.65, and the other is 0.3549. Which one is making sense and which one is not logic? Actually, it's impossible to get V out greater than our supply volt. So since our supply volt or biasing volt is VDD equals 5 volt, so we can say this value now is not accepted. So the accepted value of output volt would be 0.349 volt. So this is our output volt now, guys. So when we apply now input volt 5, we got output volt equals 0.349, which can be considered as active low. Okay, this signal can be considered, or this voltage magnitude can be considered active low signals. You know, we have a pattern for active high and active low signals, and it can be different from circuit or IC to another. So active high signal, for instance, may start from 2 volt to 5.5, for instance, for some ICs, and active low may be coming from minus 0.5 volt up to, for instance, 1 volt, like that. And the area here is called forbidden region. This is for some ICs, and this can be different from IC to another according to the circuit design. So we can consider now the voltage 0.349. It's here, so we can say 0.35 volt here is active low. So this is active low, and this can be considered active high. Okay, so we got the voltage magnitude. We need to also calculate the current. Now we can substitute in the equation to get our current. So we got V out. It's required also to check some other values. So also, since V drain to source D equals V out equals 0.3, it's less than VGSD minus VT, which is 5 minus 1. It's 4 volt. So this means our transistor is, driver transistor is in non-saturation region as we discussed initially, or as we assumed initially. So our assumption is completely right. Now, we would like to get the current now. You can get the current from any MOSFET. So let's use the simple relation, which is the saturation one, for our load. So we can say now ID equals Kn load times VGS load minus VTN load. So VGS load, you know that VGS load here equals VDD minus V out. So we have VDD 5 volt. We have V out 0.349 volt, and VTN load is given. So substitute here in the relation, you will find the current is 133 microampere. So now, guys, we could see that when we applied 5 volt, the output volt was 0.35. Here in the question, it was required to apply 2 different values. So applying 1 volt and 5 volt. So let's see together 1.5 volt. So for 1.5 volt, 1.5 volt is still less than the active high. And sometimes, guys, you may find this value not 1, it can reach to higher value. So it may be, for instance, 1.8 volt, it may reach to 2 volt. And this volt can be starting from 3 volts. So it's up to the IC. So we can just start assuming again. Since we have 1.5 volt, we can assume this value as an active low. Assuming this value is active low, so going back again to the circuit here. So if we assume that the value of the input here is active low at VI here, if this is active low, so we expect to have here active high at this time. And active high here means the voltage here across V drain to source would be high, which is going to operate this driver in active high signal. Sorry, in saturation region. So in this mode, guys, we can assume that both of these transistors are working in saturation mode. Now, let's consider this in our solution. So once we have, again, 1.5 volt, so we can say now, since we have 1.5 volt, we can assume that this is going to be low volt, and in this case, our transistor is going to work in saturation. Okay. So in this case, we can say now IDD equals IDL, that both of the transistors have the same current, and both of transistors now are working in saturation. So this is this is driver in saturation, and also our load is in saturation. So we use the same equation now. Now we can substitute with the values again. So VI equals VGSD, and VGSL equals VDSL equals VDD minus V out. So substitute here, guys, again in this relation, we will end up with our value of V out. So we got that V out here is 2.88. So 2.88 compared to the 0.34, this one can be considered active high now. We need to be sure if the transistor is working in saturation or not. So we need to check. So again, let's calculate the drain to source value. Okay. So V drain to source for the driver would be V out, which is 2.8. What is V drain to source saturation? Let's calculate it. So VGSD minus VTN equals 1.5, which is our input. So V gate to source is our input. It's 1.5 minus 1, so it's 0.5. So since we have now V drain to source is greater than the value of drain to source saturation, so this means our MOSFET is working in saturation mode. So our assumption is correct. Finally, after getting the VDS, we can now substitute in our relation in order to get the current value. So whatever the relation now of the upper or lower MOSFET, you can use any of these MOSFETs to get the current. So this would be the current in this case. So in this example, guys, we could see that the according to the input volt we applying here for this circuit, the output volt would be complement of that input volt. For that, we call this circuit as inverter. Okay. Later on, we will see the MOSFET used in logic circuits. Okay, this is one of the applications in the upcoming topics. We will see how we can use such MOSFETs in digital logic or logic gates. Okay. Now, let's make simulation in order to investigate what would be the range of control of this circuit. So, for instance, I selected one of the well-known MOSFETs used in industry, which is IRF 150. So this MOSFET is, I believe, 100 volt, and the current is around 30-something ampere. So let's see together if we connect the upper MOSFET as load and the lower MOSFET as driver, as we said, and investigate the performance of this circuit using PSpice. So I'm going to apply here a square wave. This square wave setting can be adjusted from PSpice. So for this block, guys, you need to specify the high level volt, the low level volt, the duration of on, and the cycle duration. Okay, so these parameters have to be identified here inside this block in order to make the setting and operate this transistor. So I'm going to consider the low volt as 1 volt and the high volt as 5 volt and figure out what would be the shape of the output volt here according to this supply. This mode, guys, is called transient mode. So we need to figure out the pulse with time. Okay, so transient mode, again, transient mode in PSpice is going to display the values versus time. So let's make this simulation and see together what would be the performance. So when we apply a signal of active high 5 volt, as you can see here, this is the 5 volt active high, and the active low is 1 volt. Okay, so this is 0, this is 1 volt. So as you can see, the volt or the signal has been complemented. So the active high became active low, and the active low became, the active low here, 1 volt, became around 2.5 volt. So it became active high. So this is completely right. This is considered as inverter. So when we apply active high, it would be converted to active low. And when we apply active low, it would be converted to active high. One note, when you make any kind of the applications for drivers like that, it's better to use very well-known values for active low and active high. For instance, if your circuit active high or biasing volt is VDD is 5 volt, so try to keep the active high volt very close to the 5 volt. And the active low signal, it's better to be very close to ground or 0. Okay, so I do recommend if you test or make any driver for any transistor, you need to apply active low signal as 0 volt instead of being like 1 volt like that. But here we just would like to investigate one case. So this is now, guys, called transient analysis. Now, let's investigate more and make analysis for different values of volt in order to get what's called the characteristics of our MOSFET. So the voltage transfer characteristic, how to draw the voltage transfer characteristic of our driver MOSFET. So this is again our driver MOSFET here. So this is our driver MOSFET. and we need to investigate the performance of this driver while applying variable volt. So I'm going to apply variable volt called V3, okay? Preliminary, it was 1 volt battery like that, for instance. However, we are going to use here another mode, which is DC sweep mode. So for DC sweep mode, don't care about the value here because you are going to consider this as a variable. So this here, V3, is our variable. So you need to open the setting of DC sweep and put the name of the variable here. This is the name, V3, and change this variable as you like. For instance, I started now from 0 to end volt, for instance, 5 or 6. Okay, so I wrote here 5, so, but in the simulation, this is 6. So this result is going to be for 6 volt, not 5. Okay. And I made increment of 0.1 volt, which means I will start from 0, increment the volt by 0.1 volt up till reaching to 6 volt to see the performance of this driver circuit when we change the input volt here. Okay, so this is called the voltage transfer characteristics. Nice. So the upper MOSFET is going to be connected as load. So again, how to be connected as load? The drain should be connected or shorted with gate like that. So in this case, we can say V drain to source equals V gate to source and use it in our analysis as we discussed. Now, let's investigate together what would be the shape of the output volt if we change the input volt here from 0 to 6 volt. So this is the output volt now. So this is V out, and this is V in, which is V3 as we said. Okay, so we change the volt here from 0 to 6, and the output volt will be like that. So for a signal from 0 to around 2 point something, 2.8, so almost this is 2.8. So during all of this period, the output volt is appearing like active high. Okay, it's around 2.5 volt. Okay, so all of this period, the active low was like that from 0 to 2 point something. Okay, and the output would be 2.5, which is active high for this transistor. So again, guys, the active low and active high limits or values may be different from IC to another, from MOSFET to another. Okay, so for any kind of IC, we need to check what is the active high levels or range and active low range. Okay, nice. And for the voltage greater than like 2.8 now, the output volt is decreasing, okay, until reaching to almost like 0.5 or less. So the volt here is around 0.5 volt. So if we are going to use this transistor as inverter, you have to consider that the active high signal should be from, like, in order to be very small value, like 0.5 or at least less than, let's say, 0.8, like that. So this is 0.8 volt here. So you have to make your input signal from 4.4 to 6 volt. So this range would be acceptable for active high signal to be converted to active low. Okay. Now, guys, I used IRF 150 MOSFET. This is going to be different for another MOSFET. So for that, guys, we said you have to check the characteristic of your MOSFET. What would be the active high range and what would be the active low range when you design inverter circuits. So again, we can say now, in order to be in the safe mode, consider the signal, for instance, from 0 to 2 volt as active low. So all of this as input here. So this is going to be active low in, and this is for sure the output. So this is active high output. And we can consider this range is from 0 to 2 volt. So when you input now a signal from 0 to 2 volt, it would be active low and the output would be active high. And I will stop here for this range. And let's say I will consider the range of active low to be from this point to the end of our supply, which should be, by the way, 5 volt, but I extended to investigate more. So we can say now our range of active high signal when we apply to this circuit would be, for instance, from 4.4 volt to 5 volt, like that. So this would be our range now. And we are sure when we apply the active high signal 4.4 to 5, the output would be active low, which is going to be like from 0.8 volt, even less, to 0.6 volt, like that. Okay, so this is, guys, one of the important applications we used in our life, which is inverter circuits. Next class, we will elaborate more in more circuits and applications for our MOSFETs. Tomorrow I will be available in my office, so anytime you can come to my desk if you have any question in this class, guys. By the way, I will upload the homework number 4. It will be available on eCampus. You can start solving this homework from now, okay? And the submission would be next week, I believe, the Friday next week, okay? Thank you so much, guys, and see you tomorrow. Bye.